In 3.2, we talk about differentiability, and we talked about this a little bit at the end of the last video when we were looking at those piecewise functions and trying to decide are they differentiable at that place where they come together. And so we said it needed to be continuous as a prerequisite characteristic, and then more in order to be differentiable. So we need to also be clear on where a derivative does not exist. And so we see a few examples. Any place that any function that is discontinuous is not going to be differentiable at that point of discontinuity. So that includes certainly the holes in the graph don't have derivatives at that particular place. You know, if you have a jump discontinuity, the derivative won't exist at that place where it does the jump. Any place that has a vertical asymptote is not going to have a derivative at that place, just as this crazy oscillation is not continuous, neither is it differentiable because of that oscillation there. Any place that there's a corner point, so our classic example is our absolute value of x, but we can also see that in other places we saw in that last video, you know, where we had a parabola that was joining a straight line, and that corner point made it not differentiable there because the left-hand derivative was not the same as the right-hand derivative. Any place you have a cusp is not going to be differentiable there. And the vertical tangent, so on the cusp we're thinking things like x to the 2/3, and with vertical tangent our classic example is going to be the cube root of x, something where, you know, I'm kind of trying to exaggerate it a little bit there, where you get that place where the tangent line is going to be vertical, and since tangent lines are equal to the slopes, that the derivative is equal to the slope of the tangent line, and vertical lines have no slope, then the derivative does not exist there. Sometimes it's nice to know, just for peace of mind, if nothing else, that some functions are differentiable everywhere. And so polynomials, our nicest behaving functions, continue to wear that mantle, that they behave very nicely. They're differentiable everywhere. Rational functions, that is, things that look like a polynomial over a polynomial, are going to be differentiable everywhere except where they have holes and vertical asymptotes, and those are going to be easy to identify where the denominator is 0. Trig functions behave very nicely. They're differentiable everywhere. Certainly sine and cosine are. With the others, you just have to watch out for where they have vertical asymptotes, because since they're not continuous there, then they won't also be differentiable. But anywhere else, they'll be fine. Exponential functions are differentiable everywhere. Logarithm functions, remember, they have a restricted domain. They're not going to be defined where the argument, where what's inside there is negative or 0, but everywhere they are defined, they are differentiable. They behave very nicely. It's nice to know you can do arithmetic with differentiable functions and continue to get new different differentiable functions. So adding, subtracting, multiplying, dividing, as long as you don't create a 0 in the denominator, and an even composition of differentiable functions are differentiable. I'm going to move to the next panel, and I'm going to pause it a minute, and I'm going to write something down here. So one thing that is true is that differentiable functions are said to be locally linear. So what that means is something like a y equals x squared, which is a nice smooth curve, a parabola, that even though around, say, 0, for example, is very bendy, it's got a big curve to it, still, if you zoom in around there enough, it's going to look like a straight line. And this is an important idea that we'll explore much later on too, in that it's a reasonable thing to approximate values of a differentiable function like y equals x squared with a tangent line, as long as you don't go very far away from the point of tangency. On the other hand, something like y equals absolute value of x, which is not differentiable at 0, then no matter how much you zoom in around here, it is never going to look like a straight line. It's always going to look like that V, that very sharp corner will always exist. And so that also means that since it's not locally linear, it doesn't act like a line in some small area around there, then it doesn't lend itself well to trying to approximate with a tangent line, since you couldn't find a tangent anyway because you can't take the derivative. So that's an idea that's important in calculus, and then we'll come back to much later when we're talking about Taylor series and Maclaurin series. Now, something to be aware of in the green here, our calculator uses a symmetric difference quotient, that is f of x plus h minus f of x minus h all over 2h, to approximate derivatives. Now, our calculators, the ones that are legal to use on the AP exam, cannot actually take a derivative and give you a function. So you couldn't enter in any legal calculator for the AP exam, enter in x squared, and it give you back 2x as the derivative. There are some that can do that, but you can't use those on the AP exams. So what our calculator can do with its n-deriv and the dy dx that you can access on the second calculate menu from the graph is it just gives an approximation. But it uses this symmetric difference quotient. So it will, I believe it's h is 1/1000th, but I'm not 100% sure on that. But if you wanted to approximate the derivative at, say, 5, it would actually plug in, 5 plus 1/10,000th into the function and subtract from that 5 minus 1/1000th, and then divide by 2 times 1/1000th, and whatever it got there, it's going to give you that answer as the answer for n-deriv or dy dx. And interestingly enough, most of the time that works great for us. We're going to get accuracy to usually much better than 3 decimal places, which is what we want anyway. But what happens is, because it's not doing the limit process and because it is never trying to evaluate the function or use the value of the function at the point where it's trying to find the derivative, it can give you bad answers sometimes. And so if you plug these into your calculator, I have these in yellow, the absolute value of x evaluated at 0 and so on, we know that the absolute value of x is a corner point. Its derivative does not exist at 0, but I believe when you plug that in using n-deriv in your calculator, you're going to get 0, which is then the wrong answer. And likewise with x to the 2/3, that's a cusp, which we know is not differentiable at 0, yet the n-deriv feature in your calculator will give you an incorrect answer. For the cube root of x, I believe it's going to give you 100 for an answer, and again, the derivative doesn't exist there. For absolute value of x over x, I think it gives you 1,000. Whoops, that's my left hand touching my screen. That's 1,000 again, which is incorrect. And for 1 over x squared, I believe it gives you 0. And for 1 over x, I think it gives you 1,000,000. And in fact, all of these derivatives don't exist because they happen at corners, cusps, vertical tangents, and asymptotes, and even a jump discontinuity in there for absolute value of x over x, where the derivative does not exist. So one important idea is this differentiability implies continuity. So we saw with the piecewise functions in the last video, a function might be continuous but still not be differentiable. But if a function is differentiable, it must be continuous. So it's a stricter standard to meet differentiability than it is continuity. And in that kind of a hierarchy or food chain, differentiability lies at the top of that. So I'm going to go to a new screen here, and I'm going to talk just a bit about the intermediate value theorem for derivatives, but I'm going to write it down. I'm going to pause it here and write it down. So the intermediate value theorem for derivatives goes something like this. Let a and b be any 2 points on an interval where f is differentiable. Then f prime of x takes on every value between f prime of a and f prime of b. So this kind of has a similar ring to it that the intermediate value theorem has, where remember that the IVT is a theorem about continuity. So it says if a function is continuous, then it will take on all the values between f of a and f of b. So here it has that similar ring to it. So we have some function, and we see that the derivative at a is some particular value. There's f prime of a. And the derivative of b is some other value. There's f prime of b. Then the f prime function will have to equal every value in between f prime of a and f prime of b, very much like that intermediate value theorem works. And so what that's really saying is that when a function is differentiable, so the derivative exists at every point along here in this interval, then the values you get for that derivative function are going to be connected. It's going to be a continuous derivative function. They can't somehow be very erratic and jump, from maybe one point being that slope is a -1 and jump in the next point to being +2. It can't be that erratic and that behave that weirdly. So that's something to keep in mind.